I invite you right now to expand the following three binomials. Go ahead and pause the video, multiply them out, and then when you have finished multiplying or expanding the binomials, resume the video and we'll continue from there. Now that you've finished expanding those binomials, let's go ahead and see what you got. In the first case, that one was pretty basic, something that you've seen before. Most likely you got something along the lines of x squared plus 2xy plus y squared. If you expanded part B out and you maybe moved some things around, you might have gotten x cubed plus 3x squared y plus 3xy squared plus y cubed. And in the last case, for part C, you probably got x to the fourth plus 4x cubed y plus 6x squared y squared plus 4xy cubed plus y to the fourth. And again, I invite you to pause the video, take a look at those three expanded binomials, and try to see if you find any patterns among each of those three cases. Take a look at maybe the values, the exponents, the variables. Just try to find some kind of patterns among those three. So go ahead and pause, and then when you have found as many patterns as you can, then go ahead and unpause the video. Now that you have taken a look at some patterns, hopefully you noticed a couple of things. One, the coefficients that you see in each of the cases seem to have some kind of symmetry among them. You can see it has like a pattern of 1, 2, 1, or maybe it's a pattern of 1, 3, 3, 1. Here we have 1, 4, 6, 4, 1. So you see that symmetry take place where the left and right side kind of have the same values, and as they work their way inwards, you also see that those coefficients are very symmetrical as well. Another pattern you might have noticed is that in terms of the x values, you can see that the x values start off with the highest degree, and then it drops by degrees. You don't have any more x by the very end. You can see 3, 2, 1, and then there's no x here. Here we have 4, 3, 2, 1, no x here. And then even for the y's, it looks like the y's are going in the opposite order. You can see that we have no y's here, and then we have 1y, 2 y's. No y's, 1y, 2 y's, 3 y's. No y, 1y, 2y, 3y, 4 y's. Okay, so hopefully you saw those patterns, or at least some of those patterns emerge as you were looking at the expanded binomials. Now, in terms of the actual coefficients, it is actually related to something, an idea that was formed before called Pascal's triangle. You might have heard of this before. And Pascal's triangle basically develops the coefficients of our binomials, actually. So if you have a triangle and you start off with 1 and they keep branching where 1 is always on the sides, you can actually add up the numbers and get the next value contained within it. And then as you keep doing this, as 1 goes on the side, 2 and 1 give you 3, 2 and 1 give you 3, and then you keep going with 1s on the side. And then here you can see that we'll get 4, 6, 4, 1. Notice how these numbers actually align with the coefficients that you see in certain binomials. It turns out that if you look at each row, you can kind of think of this as, this would be the degree of 0, right? This is basically the coefficients based on the degree. And in this case, this would be like a degree of 0. Here we would have our degree of 1. Here, notice when we have a degree of 2, a binomial that's being squared, that's the being squared part, we have the coefficients of 1, 2, and 1 there. So if we have a degree of 3, as you can see here, right, degree of 3, we have the coefficients of 1, 3, 3, 1, as you can see in Pascal's triangle right here. And then degree of 4, you see 1, 4, 6, 4, 1, and so on and so on. So you can just keep on going. Okay. Now we're also going to tie in the idea of Pascal's triangle, the coefficients of the binomials, with another idea here. And it looks like what we need to do is work with some combinations. If you recall, in terms of working with combinations, you can use the formula. You can say 4 factorial over 0 factorial times 4 minus 0 factorial. And in that case, 4 minus, those cancel basically. 0 factorial actually gives you a value of 1. So this is actually just going to be 1 over 1, or just 1. So 4C0 is going to be 1. The other technique I showed you was you can really just say, okay, how many items do you have? And then you put that number, total number there, right? And then you divide that by the number of items that you see there, which is, it's really just 1. So 4C1 just becomes the value of 4. If we were to do 4C2, we have 2 items, so 4 times 3 divided by, and then we take that number, 2 times 1. So we get 12 over 2, or that'll give us a value of 6. 4C3 is basically saying let's have 3 slots, 1, 2, 3, 4 times 3 times 2, divided by, and then we take that number and go downwards, 3 times 2 times 1, 3 factorial. And in that case, we see that we get a value of 4. 4C4, well, that's just going to give us 1. 4 items, choose 4. We're only going to have one way to do that. And you can see what is going on here. There's another pattern that's emerging. We still get the same symmetrical pattern, 1, 4, 6, 4, 1, that we had seen earlier, right, in Pascal's triangle, right here. Okay, so as we can see here, the coefficients are kind of actually showing us that the numbers in the array of Pascal's triangle. And then what we also saw were that the variables were either going in decreasing or increasing order, or let's say degree, depending on which variable you were referring to, the first variable or the second variable. Okay? And what we're developing is basically something called the binomial theorem. It's called the binomial theorem because if you are having a certain number of binomials being multiplied together, like x plus y to the sum power, you can basically form this really long expression with the patterns. So if we have just some basic a plus b to the n power, some very arbitrary values, right? We don't know what they are. Then the pattern that emerges is, keep in mind that the numbers are really just the array in Pascal's triangle. And we saw that the numbers can actually be formed by using combinations, because I don't think you really want to be drawing Pascal's triangle every single time, especially if you maybe have some kind of binomial taken to the 10th power. You don't want to be going all the way down to that 10th degree and finding out what those coefficients are. That would be very time consuming, right? So the other idea is, well, we have another way to get the values of Pascal's triangle using combinations. And the way we can do that, I'm actually going to color code this, okay? So what I'm going to do is I'm going to put my coefficients in one color. Let's make it blue, actually. Okay, so I'm going to put all my coefficients in one color. And I know that my first term is going to start off with NC0. My second term is going to have NC1. Basically, I just keep going down the line. I'm going to increase the order in these combinations, NC2, NC3. Notice how I'm also leaving some blanks here, because I'm going to fill it in with the actual variable values as well. Okay, and we just keep on going on and on and on. So I'll just say plus dot 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 until we reach the very end, which would be NCN. Okay, so we have our values of the coefficients. And then what we also want to do is consider, let's say, the first variable. If you notice back up above, when we looked at the binomials being multiplied over and over again, you always had the first variable, which is the first term in that binomial. You'll see x, x, right? And what did those x's do? They always went in decreasing order. So what we have here is that if our first variable here, or our first term, is a, we're going to take that a and take it to the power of n. And remember what happens to that first term. Each of those terms are always going to go in descending order. So now I went from n to n minus 1. And then I go to n minus 2. And then I go to n minus 3. Right, so it just keeps going on and on and on until at the very end, I should have no more of that first term left. I have a to the 0 power. Okay. Now, as we take a look at what happened to the second variable, as x was decreasing, we also saw that y was increasing. Let's actually do this let's do it in purple. Okay, so y was, there was no y here, but then y kept increasing, increasing, increasing. 0 y's here, 1 y, 2 y's, 3 y's. So we keep seeing that the second term, in this case the b value, is going in increasing degree order. So we have b to the, it starts off to the 0 power, and then we have b to the first, we have b to the second, we have b to the third, on and on and on until you reach b to the n power. Okay? What you actually will notice is that if you think about the degree values of the first term and last term are actually going to always add up to the value of n. So you should always see that those degrees always give you the actual degree of your binomial right there. So just keep that in mind. Every single time, they should always add up to the value of n. Okay, so just a nice little tip for you there. And then one other thing that we need to add here is that if you recall, when we had multiplied all our binomials out, we basically had to add all of our terms together. So that's what we're going to do here. We're just going to say with all of our terms, let's do this in black actually, we're going to add each of these terms together, just like that, right? And then we have the plus dot 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 right there anyway. And then just that's going to be your really long binomial expanded, and that's what we call the binomial theorem. So let's go ahead and do an example of one, okay? Let's take a look at number 3 here. So find the expansion of 3a minus 2 to the 6th power. So what I notice here, I'm just going to go ahead and classify this. I know that my 3a is going to kind of represent my first term. Again, I know that there's like an a variable here, so let's just call that an a variable. And then I also notice that my second term is going to be like, it's actually going to be like more like a minus 2, because really you're saying this is like 3a plus a negative 2, and that's taken to the 6th power. So just be aware of that, and then keep in mind that 6th power, that's kind of treated like your n value, your n degree. So as we go ahead and work this out, remember we have 3 parts to really figure out. 1, what is the coefficient? 2, what is our first term? And 3, what is our last term? So as I look at our coefficients, what I see is I have it to the 6th power. And so what I want to start off with is a 6c, and I'm choosing 0 terms, right? And what I want to do is just keep it going, 6c1, 6c2, and notice how I'm leaving blanks, because I do know that as I write these coefficients, I know that each of these coefficients have variables attached to them. So I do need to be aware, very aware that later on I'm going to have to fill in those blanks later on. And I don't have a lot of room here, as you can see. And so I'm just going to go ahead and put 6c6 down here, okay? Now that we have our coefficients covered in our binomial expanded, I'm now going to go ahead and take a look at my first term, which consists of the 3a. And keep in mind that 3a, whatever that value is, I start in decreasing order. So the highest degree you can start off with is to the power of 6. And then from there, each of those degrees go down by 1. So 3a to the 5th, here we have 3a to the 4th, here we have 3a to the 3rd, and so on, just like this. Okay, and then obviously 3a to the 0, that will just go away later on. Now, let's go on to our next term, which is, again, that's the negative 2. So I'm going to take the negative 2 to the 0 power. Then I go up in increasing degree, so negative 2 to the 1st, negative 2 to the 2nd, negative 2 to the 3rd. And again, if I'm going too fast, as you know, this is on YouTube. Feel free to just pause the video and rewind if you need to. Okay. From here, I also know that I'm adding every single term. So plus, 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 plus. Okay, so there's our binomial expanded. Now all that's left to do is actually just simplify. Okay, so let's go ahead and simplify our values. I'm going to go ahead and, again, color code these values. So 6c0, I know that's going to be a value of 1. Anytime I choose 0 things, I only have one way of choosing 0 things. I only have one way of getting that 6, so here's 6. 6c2, now it's getting a little bit more complicated, but I know that with 2 terms, I have 6 times 5 divided by 2 times 1. Here I have 6 times 5 times 4 over 3 times 2 times 1. Here, oops, I'm running out of space again. So here I'll have 6, 5, 4, 3 over 4, 3, 2, 1. 65, I didn't think this through. Here we go. we'll have 6, 5, 4, 3, 2, 5 terms, over 5, 4, 3, 2, 1. And then, oh boy, I'm really scrunched for space here. I'll have, well, that basically is just a value of 1. Okay, I'll just stick it right here. Okay. All right. I hope you have enough room on your paper. Okay. I might need to move some things around as we progress. Now I'm going to go ahead and take a look at my red terms. Let's see here. 3 to the 6th power. 3 times 3. So if we think about 3 to the 6th power, just like that, really what we're doing is 9 times 9. So that's 81 times 9. So that'll give us a value of 729. Okay, so what we'll have is this is going to be a value of 729 a to the 6th power. I do need to remember that the 6 gets distributed to both of those terms. Okay, and then in the other case we have 81 times 3, right? That'll be 243. 243 a to the 5th. Okay, and then for our next red term we have 3 to the 4th power. That's just going to give us our 81. So 81 a to the 4th. And then we also have 27 a to the 3rd. Here we have 9a squared. Over here we have 3a, and then there's nothing here. Okay, so that's just a value of 1. Okay, now let's go on to the purple. Negative 2 to the 0, that's just a value of 1. Okay, and then we'll know that we have to basically add these terms together. This is actually going to be a negative 2 plus, then we have negative 2 squared. Negative 2 times negative 2 gives us a positive 4. Negative 2 times negative 2 times negative 2 is going to give us a negative 8. And then here we have negative 2, negative 2, negative 2, negative 2. Right, that'll give us a value of 16. Positive 16. And then we're adding that to negative 2 to the 5th. Notice how, because that negative is inside the parentheses, you'll notice that every single time the values are alternating between negative and positive, right? So here we're going to have negative 32. And then finally positive 64, like that. Okay. All right, so now all that's left to do is simplify everything. So what do we got for our first term? I'm just going to go ahead and write my final answer here. So I have 729 a to the 6th, because times 1 just gives you the same value. Plus, okay, so this value is giving us this number here. And then what we have is, oh, whoops, that shouldn't be a plus, because I do notice that there's a negative sign here. So I'm going to have minus 6 times 2 is 12, and then 243 times 12. Okay, I'm going to start needing to get a calculator. Oops, why don't I actually just use my, my Desmos calculator. Okay, so what was I doing again? 243 times 12, I believe. 243 times 12 is going to give us 2,916. Okay, so going back here, I'm actually going to split, why don't we do a split screen view, and that way we can actually do our calculations and work together. So what we have here is minus 2,916, those are all of our coefficients multiplied together, times a to the 5th. And then we have plus as I move on along here. Okay, so we've taken care of this. This is all done. And then what I see is 6 over 2 is going to give me 3. So 3 times 5 gives me 15. So 15 times 4, that's 60. So we're doing 81 times 60 now. Oops. 81 times 60. Going to give us 4,860. So we have plus 4,860 a to the 4th. That's going to be all of that right there. Okay. As we move on along, 3 times 2 gives us 6. So 6 will cancel. 5 times 4 gives us 20. 20 times 8 is 160. Oh, I do notice there's a negative there. So negative, so this is actually going to be a minus sign. Negative what? 160 times, times 27. That's going to give us 4,320. So minus 4,320 a to the 3rd power. There it is. And then, so now we're going on to the next set of terms there. Okay, and then what do we have here? 4 and 3 cancel. That's nice. 6 and 2 divide out to give us a 3. And 3 times 5 give us 15. So we'll have 15 times 9 times 16. That's going to give us 2,160 Those are all positive values, so plus 2,160 a to the, looks like a second power. And just to verify, keep in mind, you should have alternating signs because of that negative that was being taken to a power, right? So you should get alternating signs, positive, negative, positive, negative. We're at positive. Now, I believe we are now looking at this value here. So notice 2, 3, 4, and 5 cancel. That just gives us a value of 6. So 6 times 3 it looks like, so 18 times 32. So 18 times 32. Don't forget you also have a negative value there. So we're going to have a negative minus 576. And then this is a to the first power, right? We just have a singular a there. And then our last one was, oh, there's just a 64, so plus 64. And right there, that is, oops, let me bring this out. So right here, this is your expanded binomial multiplied all out, just like that. Okay, and that's all there is to it, to the binomial theorem. There are a few variations of using the binomial theorem, which you will do on your own. Okay, so that'll be it for the binomial theorem.